So, in last class we have discussed Heisenberg model. And there we have seen the exchange interaction and the strength of the exchange interaction, that is we express in terms of Gij between ith and jth spin. So, that Gij is exchange integral or exchange energy constant for particular for these two. Okay. So, sometimes we take average when this exchange interaction among the nearest neighbor, then we express in terms of this average exchange energy constant, that J, right. So, when I was discussing this, I told that this that spins are, if it is ith, so surrounding jth spins are there, jth spins are there, right. So, there is interaction of jth spin with the ith spin. So, j now j equal to 1, 2, 3, 4. So, this for all j there is an interaction with this ith one. So, that is equivalent to the field, molecular field at or Weiss field. So, the way I have discussed this one, so as if they are interacting, that exchange interaction is direct exchange interaction, they are interacting with each other. So, it is a direct exchange interaction. So, there are two type of exchange interaction, one is called direct exchange interaction, Okay. So, during Heisenberg model description, the way I have described, so that is basically direct exchange interaction, directly exchange interaction among the spins or yes, among the spins or moment. So, in terms of moment J we do not tell, because special part is involved as I described. So, that is the direct exchange interaction. Second type is indirect exchange interaction, Surprisingly, it is rarely seen, this direct exchange interaction means directly interaction among the spins is not found most of the materials. So, most of the materials shows the indirect exchange interaction. So, there are very interesting this has come with time because different kinds of magnetic materials are there. When it is studied, then it suppose we should not get ferromagnetic interaction or antiferromagnetic interaction, or there should not be any exchange interaction, but it is found that it is ordered system. So, there must be some exchange interaction, and then it is analyzed and found special type of exchange interaction and given particular name. Okay. So, among this indirect exchange interaction, very famous interaction is called super exchange interaction, super exchange interaction. So, which type of material shows such exchange interaction and why it is given such name? Okay. So, it is obvious that there is no direct exchange interaction. So, it is indirect exchange interaction. So, from example you will understand why it is called indirect exchange interaction. So, this super exchange interaction, it is seen in different oxide and halide solid. As for example, this magnesium oxide and magnesium chloride, manganese, not magnesium, manganese oxide and manganese chloride. Okay. So, these materials shows antiferromagnetic ordering, antiferromagnetic ordering, Okay. So, there is either ferromagnetic ordering or antiferromagnetic ordering. So, ordering is there means there is exchange interaction, and it is antiferromagnetic interaction. So, why it is called super exchange interaction? So, in this case, so this crystal structure of this is basically manganese oxide. If I take crystal structure of this material is basically similar to the sodium chloride structure. So, in place of sodium, manganese are there, and in place of oxygen, chlorine, oxygens are there. So, if you remember the sodium chloride crystal structure, you will see that manganese ions and next manganese ions in between chlorine, in this case oxygen will be there. So, there is no manganese, So, there is a manganese, but it is too far to interact Okay. So, in between and it is not only that, in between oxygen is there, Okay. So, it cannot interact with this one manganese with the other one directly. So, because in between this oxygen is there, since this manganese 2 plus basically ions, 2 plus ions, right, oxygen 2 minus, okay, 2 minus. So, they interact, if they interact, so it has to interact via this oxygen, and that's happened. So, this manganese interact with the another manganese ions via this oxygen. So, you know this in manganese there are 5 electrons in D shell, right, 5 electrons in D shell, right. So, dxy, dyz, zx etc. Suborbitals are there. So, charge distribution of this I have shown you for d orbital, right. The charge distribution is like this for d orbitals, right. So, then oxygen it has p electron, oxygen it has p electron. So, charge distribution in p electron is like this, right, and then another manganese is here, another manganese is here. So, it is okay. So, the charge distribution of this manganese and the other one, there is no direct overlapping. So, there is no direct exchange interaction. So, but there is a indirect overlapping via this oxygen. So, this manganese here, this it basically polarize this oxygen electrons, oxygen charge, okay, and that goes to that polarize the other one. So, that way, or just simply you can tell that there is a overlapping of the charge of this oxygen with this manganese and with the other manganese, thus they interact with each other, these manganese ions interact with each other via this oxygen. Okay. So, this type of exchange interaction is called basically super exchange interaction. Okay. So, generally this type of super exchange interaction is found in ionic solid. So, it is found in ionic solid, okay, in ionic solids. So, second type of exchange interaction, so like manganese oxide, manganese fluoride, etc. So, these are antiferromatic, this super exchange interaction basically antiferromatic exchange interaction, and this manganese oxide, manganese fluoride, they are antiferromatic material. Okay. So, this now question is this iron, cobalt, nickel, etc. They are metal basically, they are metal, and in solid, in pure iron material, in pure cobalt material, in pure nickel material. So, atoms are at lattice point. So, even they do not interact directly, their charge distribution are not directly overlapped. Okay. So, they also interact indirectly. So, in case of metal where conduction electrons are there, in that case the type of exchange interaction is found, that is called RKKY, or itinerant spelling mistake, itinerant, yeah, there may be spelling mistake, but it is itinerant, conductive, itinerant means conductive, itinerant exchange RKKY or itinerant exchange interaction. So, these are antiferromagnetic interaction is found, antiferromagnetic. So, RKKY or itinerant exchange interaction okay. So, this is found in case of metal, okay. So, here so this RKKY, it is basically after name of this Ruderman. So, they discovered this exchange interaction, Ruderman, Kittel. That book I have given as a reference, Kittel and then this is Kasua and Y is Yoshida. Okay. So, after this 4 name, so their first letter is used RKKY exchange interaction or itinerant exchange interaction. So, that is found in case of metal where conduction electrons are there. So, basically conduction electron conduct this exchange interaction among the spins or yes, among the spins of metal. So, this spin of ions basically, not spin of electrons, spin of. So, in lattice, basically in lattice we have with ion this we have spin right. Now, its metal, it has electron, conductive electron. So, they do not interact directly, they interact via this conductive electron. So, it is telling that so this spin it polarizes this electron, and when this electron are moving all the time, right, conductive electrons. So, it is free electron kind of things. So, it polarizes this electron and that information goes to the other one. So, it also it polarized as per its state, and that polarization that goes to the other one. So, via this electron its state of polarized, the state of its state, according to its state, it influenced the other one, this other one. So, that way via this conduction electron, the lattice site, the spin of ions, they are interact with each other. So, that is called basically RKKY or itinerant exchange interaction. So, it is found in this type of interaction is found in iron, cobalt, nickel, right, gadolinium. So, gadolinium, iron, cobalt, nickel, these are basically metal, these are transition metal and this rare earth metal, and this shows the ordering because of this type of interaction. Now, which type of ordering we will see, that depends on the distance between this lattice distance. So, it is very this interaction, this ordering is very sensitive to the distance, lattice distance, and depending on the lattice distance. So, this it decides whether it will be antiferromagnetic or it will be ferromagnetic. So, if you so as you know that exchange integral, exchange energy constant, okay, or RKKY. Okay. So, this exchange generally we write RKKY type of exchange interaction. So, this is the so if you plot this one, as a function of or distance between the lattice points. Okay. So, then it is found it is oscillatory behavior, it shows the oscillatory behavior, means it is this kind of this oscillatory behavior is seen. So, what does mean? So, this side is positive, this exchange interaction this positive, and this side is negative, So, when this J exchange integral is positive, so then it is ferromagnetic interaction. If it is negative, then antiferromagnetic interaction. So, in case of this here chromium, manganese, okay, pure chromium, pure manganese. Okay. So, in case of I think chromium and then manganese, yes. So, this for chromium, this for manganese, okay, and this for iron, this for cobalt, this for nickel, this for gadolinium. Okay. So, this is the strength of the exchange interaction. So, these are negative and their distance, in case of chromium that is the distance, in case of manganese that is the distance, iron that. So, depending on the distance between these ions. Okay. So, this value of this exchange integral it changes and its sign also changes. So, from this one can tell this chromium and manganese is antiferromagnetic and iron, cobalt, nickel, gadolinium is ferromagnetic material. Okay. Ferromagnetic interaction or ordering is found. So, these are ferromagnetic, these are ferro and these are antiferro. Okay. So, it is very famous exchange interaction, and this why this chromium and manganese shows the antiferromagnetic ordering, whereas they shows the iron, cobalt, nickel shows the ferromagnetic ordering. So, it is nicely explained using this exchange interaction. Okay. So, thus yeah. So, this next type of exchange interaction that also very popular, very useful one. So, that is called double exchange interaction, double exchange interaction. Double exchange interaction. Okay. So, if you take lanthanum, if you take lanthanum manganate, okay, LaMnO3, or strontium manganate, then these two materials shows the antiferromagnetic property. These two materials shows the antiferromagnetic property. So, their exchange interaction is basically super exchange interaction. So, this I told this some oxides is generally insulating material, and they shows the super exchange interaction. So, they shows the super exchange interaction. Okay. Both are antiferromagnetic, and their exchange interaction is super exchange interaction. Fine. Now, here this lanthanum is basically its valence is 3 plus, and strontium is 2 plus, strontium is 2 plus. Okay. So, in this case the manganese, so valence is 3 plus, right. So, 3 plus, so oxygen 2 minus, so 6, so here plus 6. Okay. So, strontium 2 plus, so manganese will be 4 plus, and then oxygen 2 minus, so 6, here 6. Okay. So, now if you dope this lanthanum manganate with the strontium, dope means if you put some strontium in manganese in this lanthanum manganate, and some strontium will replace lanthanum. So, that metal we write in this way, lanthanum, it is not lanthanum 1, manganese 1, oxygen 3, this ratio. So, lanthanum now less than 1 by X fraction, and strontium occupied this X fraction, then manganese oxide. Okay. If this is the material, so in this material here it is 3 plus, here it is 2 plus. So, some manganese will be 2 plus, will be 3 plus, and some manganese will be 4 plus. Okay. So, the amount will be decided 3 plus 4 plus by this X, right, and 1 minus X. So, that means in this material mixed valency are there of magnetic ions, mixed valencies are there of magnetic ions, and for such case this now lanthanum strontium manganate is ferromagnetic. Now, it is very interesting, it is when this lanthanum manganate, strontium manganate, they are antiferromagnetic. When if we mix them together and getting this material lanthanum strontium manganate, so it shows the ferromagnetic. So, these two are antiferro, and exchange interaction is super exchange interaction, whereas these are ferromagnetic, okay, and ferromagnetic or ferrimagnetic, whatever, because their spin are different. Okay. I think it is ferromagnetic anyway. So, so here we are getting ferromagnetic order. So, how this is getting? So, that is telling that it is getting via the double exchange kind of exchange interaction. What is that? So, if you so in case of, I think I will Up to here I can tell you here. So, manganese 3 plus means 4 d electrons are there. Manganese 2 plus have 5 d electron. Now, 1 electron is goes over 4 electrons, d electrons, and manganese 4 plus will have 3 d electrons, right. So, in crystal field, this as I has told you that Eg and T2G type of energy levels. So, 5 energy levels due to crystal field, that 2 are 2 and this 3, this T2G, I think T2G, yes, and this is Eg. Okay. So, this separation because of crystal field earlier I have discussed, and that is for if this is for manganese 3 plus, means 4 electrons are there. So, this in this level, so in each level 1. So, this energy are same, and another will be here, okay, another will be here. And for other case, manganese 4 plus, so here 3 electrons, so this here 3 electrons, so 1, 2, 3, right, according to Hund's rule. So, we placed it, and here there is no electrons, right. Now, this 3 plus and 4 plus, so this is the arrangement of the spins. Now, here this spin, it can go here, okay, it can go here, when it is going here. So, this vacant, now it can again come back here. So, this way is hopping, it is called hopping, it's goes from here and then. So, exchange between that Mn3 plus and Mn4 plus ions, magnetic ions, via this hopping. Okay. So, this exchange, so this type of exchange interaction is called double exchange interaction, and because of this exchange interaction, it shows, this material shows the ferromagnetic ordering, and for that basically we need mixed valence state of magnetic ions. So, here it has two valency, 3 plus and 4 plus, and that is why this type of exchange interaction is possible. And because of this exchange interaction, it is ferromagnetic ordering, and this is called double exchange interaction. Okay. So, mainly these are the main exchange interaction in ferromagnetic, antiferromagnetic ordering. Yeah. So, I think whenever you will study material, magnetic property of the material, so you can find out exchange interaction among them, which mechanism it is following, which interaction it is following. So, in terms of that one should. So, here whatever the common material, this is the common material. Okay. So, these or other materials, that their exchange interaction will be out of one of them, or there are some special interaction. So, that we will not discuss, but these are the main exchange interaction. So, I will stop here. Thank you.